Hi, everyone. Today, we're going to talk about regression and reliability. And we're kind of condensing the lecture and lab for this video. I'm going to walk through what these things are, why they matter, and what we do with them conceptually as a lecture. And then I'm just going to seg over to the lab part, where I will show you fairly briefly in SPSS how we do these. Now, why is it going to be fairly brief? Well, for this particular class, you're not actually doing these in SPSS. What you're doing is you're interpreting output. And because of this, I want to draw your attention to a few different things in D2L before we launch in. So I first need to share my screen. That is always helpful. If we jump over to D2L, you can see that there's a module called SPSS Guides. If you click on this, you'll see that there's guides that's an SPSS refresher, scales, alpha regression, and reliability in SPSS, multiple regression, moderation, and mediation. If I open up one of these, it gives you directions, gives you a purpose. In bold, there's directions on what buttons to hit in the menus to get to this, and what to do. So you might see here that there's an example of how we recoded variables. Down lower, it's how we do scale scores. There's a reliability one. And then some of these guides, many of these guides really, have an arrow pointing to relevant parts of the output that you need to interpret it. This may be particularly handy for you if you're sitting there and you're looking at your homework and at the output and thinking, shoot, I don't remember exactly what I need to look for. These arrows are a good way to look at and find what you need. So there's guides on here that will correspond to every homework that you're going to have to do, and I highly suggest that you refer to them if you need it. One other thing, we'll go back. There's another module here that's called Homework and Output. This is where I'll post assigned homework and the associated output with it. The output will be in .htm form, so you can open it in a web browser and view it without SPSS. That should hopefully, again, allow you to do the homework without actually having SPSS, to save that step as we're online, and that's more challenging. So with that all said, what we're going to do is we'll talk about regression, we'll talk about reliability, and then I'll walk through an example or two for each thing with your data sets that you're using for your projects. The reason I'm doing this is throughout the class, I want to be able to walk through some of the output that you're going to see for your final project so you know what it is you're looking at and how to interpret it. Again, we're just making that runway a little bit longer for you, but we're going to start with regression. And regression you could think of as an offshoot of correlation. So just as a reminder, correlation is just what's the nature of the relationship between two variables? How strong is that relationship? And what direction is it? Is it positive or negative? Regression takes a similar framework. It lets us, but it adds one thing. It lets us predict one variable from another. This is really useful because a lot of times in psychology, we want to say how much is one thing going to predict another. For example, how much is conscientiousness going to predict job performance? How much does job satisfaction predict turnover? And so on and so forth. Most of the questions we have in IO psychology are prediction-based questions. And as a result, we rely on regression and offshoots of regression 85% of the time, I'd say. Most of the time, certainly. So it's really important to cover. So we talked about correlations. You have positive relationships and negative relationships. This is just a review from the previous slides. We measure Pearson's correlation with the Pearson's R. And remember, it ranges from -1 to 1. Now, when we move to regression, we throw some of that out. We still have the positive and negative, but it's no longer limited to -1 to 1. Instead, what we do is we get an indication of how much or how well one variable predicts another. It's used, and don't spend too much time on this, please, but it's basically, if you remember back to math in middle school or high school, the y equals mx plus b, figuring out the slope and the intercept of a graph. That's basically what regression is. What we want to do is put a line that explains the most in our predictor. We want to explain the most we can, explains the most in our dependent variable for our regression. So we're basically doing y equals mx plus b. It's just rearranged here because statistics has to do it different. But it's important because it lets us understand how well we're predicting our dependent variable with our independent variable. So think of it this way: a perfect predictor would explain 100% of the variance in an outcome. That's what we're always chasing. It doesn't exist in IO. But think about it. If we could perfectly explain job performance with whatever it is, we would just hire in that thing because that thing is the only thing leading to job performance. Now, it's rarely that simple. Oftentimes there's multiple variables in play, and we'll talk about that when we talk about multiple regression, mediation, and moderation. But the fundamental question we ask is, how well are we explaining y with x? And that's sort of the goal, the metric we use. How much variance are we explaining? So in your homeworks, one of the main questions will be, what is your R squared, or your coefficient of determination? In other words, how much of y are you explaining with x? The more you're explaining, the better predictor you are, the better model you have, right? Because if you think about it, if we have a bunch of good predictors, we want to explain a lot about job performance. If our predictors suck, we're not explaining very much. Why are we bothering? We go back to the example about high school or college admissions, rather. Colleges often look at SAT scores and high school GPA. And the reason they do that is because the R squared is high. It's because those two things, especially GPA, explain a lot about being a good college student. So if our DV is college GPA and our IV is high school GPA, we're explaining a fair amount of variance, which makes sense. If you're a good student in high school, you are more likely to be a good student in college. And again, we're not saying that if you're a good student in high school, you will be a good student in college, or if you're a bad student in high school, you will be a bad student. But generally speaking, that's fairly true. People improve and all that, but it's the best predictor we have. And it's things like regression that allow us to pick those predictors. There's a lot of stuff we don't use as much. The reason we pick GPA is because the R squared is so high. So one thing regression lets us do is pick predictors to use that are meaningful, which then lets us ignore predictors that are not meaningful. How do we tell if a predictor is meaningful? We look at this R squared. How much variance in Y are we explaining with X? And then there's the inverse of that, this coefficient of alienation. How much are you not explaining? How much of Y are you not explaining with X? So I really like this diagram here. We have X and we have Y, and the overlap between those two variables is our R squared. This overlap here that my cursor is hovering over is how much of this, if you think of Y as like this big pie chart that we're trying to explain, it's the percentage of that pie chart that we know and can explain. And then the rest of it, we don't know. We don't know what's leading to that. So sometimes, a lot of times in IO psychology, our R squareds aren't that huge because there's so many factors. In some other fields, I have some friends that work in like safety crash testing. They have massive R squareds because they use equations like how well does seatbelt usage predict vehicular fatalities. Seatbelt usage is a massive predictor of whether or not you survive a car crash. We don't deal with things that are that extreme in IO psychology, but we look at the same thing. When I talk to my friends about their work, we're still asking the same questions. What's the R squared? How much variance are you explaining? So now that I've maybe beaten that horse a little to death, let's talk about what affects the size of your R squared. What affects how much variance you're explaining? One thing is restriction of range. So you want to be measuring along the full ability level, right? If we're testing for intelligence on something else, but we're only looking at first and second graders, it's going to be a very different relationship than if we looked across the K through 12 spectrum. Again, by the way, these things just kind of know like that they're issues conceptually. You don't have to worry about them too much. But if you look at only a very particular range of your sample, let's say I'm looking at college admittance and GPA in high school to GPA in college, but I'm only looking at people that go to like a Harvard or Princeton. That's not the best test of this because they probably all had 4.0s in high school. So we're not getting the full explanatory power. It doesn't let us fully understand how much one thing affects the other. At a place like Radford or Virginia Tech, when there's more range in GPA, then we can better understand how much high school GPA affects college GPA. Restrictions of range on a third variable can affect things. So if you're looking at the relationship between memory and mental health, how good your memory is affect your mental health? It could be, if you're looking at only people that don't use drugs and don't drink, you could have a really great relationship there. But you're restricting your range. You want to look at as broad a range as you can. It may be that relationship between memory and mental health is less strong when you include people that use whatever substance that might affect their memory. So not only do we have to worry about range restriction on the variables we're looking at, we have to worry about it on potential third variables. It matters a lot whether we're looking at everyone together or subgroups. If you look at this left-hand graph here, that's a correlation between education and salary, I think. Yep, education and salary across everyone. And it's not a super strong correlation. But if you look at it and separate it by gender, it's a much stronger correlation. So sometimes group membership affects the size of your correlation and your R squared. If you have groups that you think are meaningfully related to your variables, you might want to take that into account. Unreliability in your X or your Y measure, remember reliability is consistency. So if your measurement is inconsistent, it's going to screw up your correlations. You need reliable measures, and we'll come to that in just a minute. And then, of course, the actual relationship between X and Y. Whatever it is in real life, that's the biggest driver. So all these things can kind of futz with your relationships, but the big take-home point here, and there's marginal distributions, we're not going to get into that too much. The big take-home point here is there's factors that affect the size of your correlation and thus your regression. But we do regression to predict one variable from another variable or multiple variables. What do we care about there? Well, we end up caring about some things we'll talk about in the output, but the main one is our R squared. How much variance are we explaining? And then we can look to see if the predictors are significant. I mentioned reliability just a second ago. That'll be the second thing we go to. And it's something that, if you ever read like an academic journal article, it's something that a lot of survey studies report because they want to say, this is how consistent our survey was. And we talk about reliability in different ways. We talked about this in the research methods lecture. There's iterator, test, retest. The one we care about is internal consistency. This is how much are items on a test like one another? So when we do this, we want to look at the reliability for the items that correspond to each construct. If I have 3 items for job set, I'm going to look at reliability over those 3 items. And that gives me my reliability for job set. If we have 5 items for job motivation, I'll look at those, and this is really key, I'll look at those separately. We get reliability for every different scale we have. So in your projects with variables like stress and satisfaction and work-family conflict, you'll want to report reliability for each one of those separately. And in the output you get, you'll see that. In this case, we measure reliability with what we call Cronbach's alpha. And this is kind of an easy thing. We look at the alpha, and then we use rule of thumb cutoffs. Over 0.9 is good, very good. Over 0.8 is good. 0.7 is the cutoff for acceptable. If reliability is below 0.7, it really makes you question how trustworthy your results are. That's why we report it. It lets people make a decision like, oh, your reliability was good, we can maybe trust your results more. Oh, maybe your reliability was really bad, maybe we don't trust them as much. So it's kind of like a quality benchmark of your scales that you use. And again, when I say scale, I mean the items that correspond to a particular construct like job satisfaction. So that's really reliability in a nutshell and regression. What I'll do is walk through this in SPSS and do a couple examples of each. So what I have up here in SPSS is your data sets for the summer. Whichever question you're doing, you're pulling it from this data set. And you'll notice at the end, I've created job stress, job sat, intent to quit, and work family variables. And I've done that by reverse coding what I need to and creating those composite scores that we talked about. So let's start with a regression example. How do we do it? And what do we look at? Let's start with something pretty basic. Does job satisfaction predict intent to quit? So job sat is our X variable. Intent to quit is our Y variable. Let's try this. So I'm going to go to Analyze, Regression, which makes sense. We're doing a regression. And then we're going to do a linear regression. This is the most common type of regression that's done. And it brings up this fun box here. So remember, I had said job satisfaction is our X variable or independent variable, and intent to quit is our dependent variable. Let's try this. I scroll all the way down. I'm going to move job satisfaction to independent and intent to quit to dependent. And that's it. That's all you have to do for a basic regression. Then you can hit run. And then I need to find where my output went. There we go. You get kind of a short piece of output here. I want to draw your attention to 2 really important things. The first thing we look at is under model summary. And we look at the R squared under model summary. For this example, it's 0.274. That means we've explained 27.4% of the variance in Y. Put in more concrete terms, job satisfaction explains 27.4% of intent to quit. That's pretty good. You know, it's not explaining everything about why people quit, but it tells us job satisfaction leads people, or the lack of it, leads people to intend to quit. So that's thing 1, the R squared. Thing 2 is looking at our predictor to see if it's significant. We do that by going down to coefficients. Our predictor was job sat. And then we look at, and This confuses some people, so I'm just going to say you can report either one, your B weight or your beta weight. Your B weight is unstandardized, your beta weight is standardized. For those of you that remember 301, it's like your beta weight is Z transformed to be standard. I'm fine with you reporting either. But if we look at our B weight, it's negative 0.386. The corresponding beta weight is negative 0.524. Pick one or the other. Again, it's up to you. And the p-value is 0.000. Remember, in SPSS, that sig value is the p-value. And 0.000 doesn't mean it's zero. The way that SPSS does things is it means it's just so small that it's less than 0.001. But what it tells us is it's significant. So JobSat is a significant predictor of intent to quit because of this p-value. You'll notice that the B weight and beta weight are negative. That means as JobSat goes up, intent to quit goes down. That makes sense. If we had a positive relationship, it would actually be very confusing. So more JobSat leads to less intent to quit because of that negative relationship. And our R squared is 0.274. That's it. That's regression. Let's do one more example. Let's see how job stress predicts intent to quit. So we're going to do a regression, same thing. We're just making job stress our independent variable and job or intent to quit our dependent variable. So again, I'm going to go to Analyze, Regression, and Linear. And I'm just going to swap out JobSat for job stress. So now job stress is in our independent variable box. And we'll hit run. Okay. Now think for a second. What do we look at here based on our last example? Well, the first thing we look at is our R squared. It's 0.017. That's 1.7% of the variance. It's interesting, if I scroll up here, so JobSat was 0.274. Job stress is 0.017. We can already tell JobSat is a much better predictor of intent to quit than job stress is. We can just compare those R squareds and see that one predictor is better than the other. So that's the first thing we look at. What's the second thing? Your B weight or your beta weight. It's positive, which means more job stress leads to more intent to quit, going in the same direction. That makes sense. And it has a p-value of 0.092. Now, is 0.092 greater than or less than 0.05, our cutoff for significance? It's greater than, right? 0.092 is more than 0.05. So job stress isn't a significant predictor of intent to quit. So just in two pretty quick analyses, we've learned something interesting. Well, we've learned a few things interesting. One, JobSat is a pretty good predictor of intent to quit. The more satisfied you are, the less likely you are to quit. And we've learned that job stress is not a good predictor of intent to quit. It's not significant, not a good predictor. So if you can take this a step further and ask yourself, if you're a manager or part of an organization, you have a turnover problem. If I looked at this data, I would say, let's really focus on improving job satisfaction. Job stress isn't leading people to quit. Lack of job satisfaction is, so that's where we can focus our efforts. And that, folks, is how we do data-driven decision-making in organizations. We collect data, we look at it, and then we provide recommendations or do something in order to use that data to make the best decision we can. In this case, we'd say, let's work on JobSat. That is regression in SPSS. We're going to do one other thing. Remember, we talked briefly about reliability. We're going to look at reliability for JobSat and job stress items. Remember, reliability is consistency. We want to look at Cronbach's alpha, and we want it over 0.70 as kind of a check mark of like our reliability was good or our reliability was bad. If for your projects you get bad reliability, that's something to talk about in your discussion of saying, well, we got significant or non-significant results, but you should know our reliability was bad. Be careful about your interpretation. So let's get reliability for JobSat. Like before, we go to analyze, but now we go to scale and then reliability analysis. And in this case, this is really important. We don't just put in that big JobSat variable. Do not do that. We have to put in the items. In this case, SAT 1, 2, and 3. So we'll do this once for JobSat and then once separately for stress. You always do them separately. So you pull the items that correspond to that construct in, run it, and we see here under reliability statistics a Cronbach's alpha. In this case, our Cronbach's alpha is 0.947. So that's good. That's well above 0.7. We have good reliability. We can trust JobSat. Now let's do it for job stress. Oh, went to regression by accident. Analyze, scale, and reliability. I'm going to take these out and put in the job stress items. There's 5 of them, JS1 to JS5. And okay, we get a Cronbach's alpha of 0.77. Now, this isn't nearly as good as the 0.947 that we got for JobSat, but it's not bad. It's still above 0.7. It's still acceptable. So we can trust our results with job stress. And folks, that's it. Just to recap, we talked about what regression is, what reliability is, how to do it, and what to look for and report in SPSS. And last but not least, I'll introduce your homework on this topic. It's called the regression assignment. I'm giving you guys, by the way, a different data set, which we'll talk about here quick. It's called Basic IO. It has SAT, motivation, involvement, and intent variables in it. So if you look at this data set, there's all the items, then there's the composite scores, and there's also some demographic items. So this is the data set you'll be using for your homework. Just gonna say that one more time. This is the data set you'll be using for your homework. It'll be on D2L under data sets, and there will be output. For your homework, I'm going to ask you to report alpha for JobSat and for job involvement. And then you're going to interpret 2 regressions, kind of like what we did just now in the example. One where JobSat is predicting intent to quit, and one where we're using job involvement to predict intent to quit. And then lastly, just look at those R-squared values and see which one was better, which one was higher. The higher R-squared value identifies the predictor that accounts for more variance. Just like we did just a few minutes ago, where we saw that job satisfaction had a higher R-squared than job stress. And that's it. That's your homework. All right, folks, thank you for tuning in. Please let me know if you have any questions. That's all in regression. Next up will be multiple regression. So hold on to your hats. Take care, everybody. I'll stop my screen and